Hey, for section 2.8, we are looking at the derivative as a function, which actually we did in 2.7 as well, though in 2.7 we were looking specifically at the derivative at a specific point, like we were finding the equation of the tangent line, and so we were evaluating at a specific point. This time we're going to leave the derivative in terms of x, so that way it is like a formula for finding the slope at a given point. Okay, so for the derivative, recall that the derivative is defined here. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Other notation, so f prime of x, sometimes we just do y prime for short. Leibniz notation, dy dx, or sometimes df dx. Those are the most common. So if you're asked to use the definition to find f prime, this is what we mean. We mean to use the limit definition. So for example, if f of x is x plus root x, then f prime of x is going to be the limit as h approaches 0 of x plus h plus square root of x plus h. Here's the f of x plus h. We're replacing x with x plus h. And then minus x minus root x all over h. So this simplifies a little bit. So notice here that we've got the x minus x. So those are gone. And then what we have left over, I want to write it as, I want to look at the h over h separate from the square root of x plus h minus square root of x over h. And I better put parentheses around that because it's more than one term. So the reason that I broke the fraction up into two pieces like that was so that the conjugate would make some sense. If we have three terms, then we would have to do grouping, and since we have two different square roots here, we really needed them to both, in order to make them both go away, we're going to need to separate it like this. So what I'm going to do here, this is actually like inside the parentheses, I'm going to multiply by the conjugate. Let me go ahead and change the color here to square root of x plus h plus square root x over square root of x plus h plus square root x. So then what we end up with, limit as h approaches 0 of 1 plus, now we're multiplying top and bottom by the conjugate. So in the numerator, we get just x plus h minus x. And in the denominator, we get h times square root of x plus h plus square root x. So once again, these x's reduce, or they add to 0. And additionally, we have this h and this h. So we're left with h over h there. So those reduce. And let me rewrite this. So we have 1 plus 1 over square root of x plus h plus square root of x. And now we don't have the problem that we were having before where we were dividing by 0. So we end up with, when we put in our 0 for h, we end up with 1 plus 1 over the square root, 2 times the square root of x. Okay. For my second example here, let's find the horizontal tangents. Of f of x equals x squared plus 4x minus 1. Okay. So a quick note here about horizontal tangents. So let me just draw kind of a generic function. So this is not f, but I want to show you really quickly. So I'm just going to draw a function like this. This looks like a cubic function. But horizontal tangents, so if we're looking for horizontal tangents here, they're going to happen when the curve is either at a max or at a min. Okay, so for optimization problems, and we do them later when we want to know the max and the min, those are kind of the most important features of a graph. For instance, if we have some sort of formula, if we have a function that models profit, we want to know where the maximum profit occurs. And if we are doing something in engineering and we want to know like what the maximum stress of something is, then those are often figures that we need to do or need to find. So when a tangent is horizontal, okay, that means that its slope is 0. So to find the horizontal tangents, you just need to find the derivative and set it equal to 0. So let's go ahead and do that for this function. So f prime of x is equal to the limit as h approaches 0 of x plus h quantity squared plus 4 times x plus h minus 1, then minus x squared minus 4x plus 1 all over h. Now we need to do some algebra and clean this up. So we're going to have x squared plus 2xh plus h squared plus 4x plus 4h minus 1 minus x squared minus 4x plus 1 all over h. And now let's see what we got to cancel. X squared minus x squared. You can kind of work back here because everything that doesn't have h in it should go away. Minus 4x and plus 4x. And then the plus 1 and the minus 1. And so what we're left with, everything has an h in it. So we can divide by h and eliminate the h in the denominator. And so what we're going to get is 2x plus h plus 4. And when we let h go to 0, we're just going to get 2x plus 4. Okay, so back to the original thing, we needed to set f prime equal to 0. So we're going to set 2x plus 4 equal to 0. Solve that. And we get x equals negative 2. So this is just one horizontal tangent. At x equals -2. We can look at what the graph looks like. We really should already know that this is a parabola opening up. And without really having to do much else, we know that the vertex is happening here, because we know that parabolas are going to have a horizontal tangent at the vertex. So at x equals -2, we probably should find the vertex. Let's see. Well, we know x. Let's see. What is f of -2? If we plug that in, we're going to have 4 minus 8 minus 1. I'm plugging in from that function there, which is going to be -5. So that tells us, if I make this scale 3, 4, 5, then here's our parabola pretty much. And you can see that the horizontal tangent is going to be right here when x is -2.